Okay, guys. So as I explained before, I told you what you have to learn in this course is logic circuits. Okay, and when the time comes, you will understand. For example, I can make logic circuit to do addition, to do subtraction, to do multiplexing, to do decoders. So there are a lot of some functionality we need in the logic circuit. But this is the purpose of the whole course, is to design logic circuits. Is that okay? We agree on that. Also, so as I told you last time, in logic circuits, you have inputs, binary inputs. For example, you have X, Y, Z, and then you have here output, for example, if, and you have a function here. Okay, so for example, if here, the output here is actually, I can say it's a function of X, Y, and Z. Okay, and in this function, as I explained, we use three main operations. We use not, we use and also we use or operations. Is that okay? And then I told you here in these functions, we're gonna use what we call Boolean algebra. Okay? As I explained, there are some similarity and also there are some differences between the algebra you learned before and the Boolean algebra we are using here. Okay, and then in this section, I explained the characteristics, the theorem, the properties of Boolean algebra. Okay, so I explained all of them. So we have here some rules. You need to know all these rules, and then we will see. So these are all rules. I can use it in case of Boolean algebra. Okay, you need to know them. And then here in this section, I'm going to teach how can we use the Boolean algebra, or how can we call it algebra manipulation. How can we do algebra manipulation so that you can prove equivalence or you can simplify a function? Okay, so I'm gonna elaborate in this section. So what do you mean by equivalence? I already told you about it, but I can explain it again. So here, equivalence means if you have two functions or if you have two expressions, okay, I wanna prove if they are equal or not. So you have two expressions, okay, for two circuits. Maybe these two expressions are going to do the same thing. So these two circuits are identical. They can do exactly the same thing, but by a different way. You get what I'm saying? So here I do one AND inverter, and then I do OR here. So if you design a circuit this way, or you design the circuit this way, it will be identical. Okay, so any one of them will do the same job, okay, or the same functionality. Okay. So as I told you before, this is what we call equivalence. How I can prove two expressions are equal or not. Okay. So I told you to do that. There are two ways. Maybe the very easy way is just use truth table. Okay, and that's what I did here. So in the truth table, here in these two terms, how many variables you have? I can see A and B and C. So you have three variables here, A, B, C. And then here I write here all possible cases. All possible cases for A, B, and C. Okay. And then I need to calculate this term. Also, I want to calculate this term. Okay. But to calculate this term, I need to find B prime. Also, I need to find AB prime. Okay, that's what I did. So here I calculated B prime. Again, I just did this one to help me to calculate this one. to calculate this term. So anyway, I calculated B prime. B prime here is exactly like B, but I just flip. 0 becomes 1, 1 becomes 0, and so on. Okay. EB prime, so it's easy to calculate it because I have A here and I have B prime here. It's easy to calculate. And I told you how we can calculate it. Okay, listen to me. The easy way in case of N, look for zeros. Look for zeros. Okay. So here we have 4 zeros. Okay, I don't need even to look at this one. 4 zeros, so I should have 4 zeros. So very easy. Okay, and also here I have 2 zeros. So this one 2 zeros right away. I don't need even to look at this one. Okay, and the only way to get one, so we have 1 here and 1 here. Okay, by this way I was able to calculate EB prime. Okay, now I need EB prime or C. So I have this column here and I have C here, this column here. So I'm going to do OR between this column and this column here. And as I told you before, in case of OR, look for ones. When one input is 1, you don't need even to look at the other input. The output is 1. Okay, and that's what I did. So you can see here I have 2 ones. So it should be 2 ones here. Okay. Here we have here 1. So it has to be 1 here. Okay. We have here 1. So it has to be 1 here. Okay. We have here 1. So it has to be 1 here. The only way to get zeros is actually when the 2 inputs are zeros. Anyway, so after that, I calculated the first term here. Now I want to calculate the second term. To calculate the second term, I need to do this. I need to make a column for this one, and then do AND. So that's what I did. I have AND here. Sorry, I have A here. I have C. So all what I have to do AND between A and C, and this can create this column here. Okay. Also, I have here B prime. I have C here, so I can do OR. Sorry, this is OR. I can do OR between them and then get this one. Okay. Once I have this term and this term, I can do AND between these 2 terms to get this one. Okay. So now I'm gonna compare this term or the outputs of this term to the output here. Okay. I can say these 2 functions or these 2 terms are identical or they are equivalent only if these 2 columns are identical. Okay. So here, if you find only one difference, so here, if you see here, we have 0 and 0. Okay, 1 and 1, 0 and 0. So it's identical. Okay. Okay. By common sense, by intuition, if you have 2 functions and these 2 functions give you the same output for the same input, so this should be equal. You get what I'm saying? So for the same input, for all possible cases for input, for the same input, it gives you the same output. So they should be equal. Okay. So this is one way to prove or to check if 2 terms are equivalent or not. So what you have to learn here, guys, it is possible that the same logic circuit can be implemented or can be designed by different ways. And that's exactly what we did here. These 2 circuits are identical, but here I did it using AND and OR. But here I did it using AND and then OR and OR. You get what I'm saying? So it's possible 2 different circuits. The same circuit I can implement it by different ways. Okay. So this is one way to prove they are equivalent. Maybe this is the easy way, or the systematic way, or the straightforward way. There's another way, and you need to learn it. Okay? One way is not enough. So in exams and quizzes, if I ask you, if I told you there are 2 ways, right? So you can do algebra manipulation. So as I explained before, you can take one term, either this term, and then you can do algebra manipulation to get this term, or you can take this term and you can do algebra manipulation using the theorem I explained before to get this term. Okay, so that's what we call using algebra manipulation. You need to know that both of them. In exams, in quizzes, if I don't tell you which approach you have to use, you have the choice. Okay, so if I just prove, if I tell you just to prove this one is equal to this one, and I didn't tell you using truth table or using algebra manipulation, so you can use either way. Okay, but I'm expecting you have to learn, you have to know, because I'm quite sure 100%. If I give you the choice, 90% of the student will take this one because it's easy one, but still you need to know algebra manipulation. Okay, so you need to know the rules, you need to know how to apply them. Okay, so that's why I may ask you to use this one. Okay, or what you can do is I in one quiz last semester, some student did it using algebra manipulation, and then you want to check if it is true or not, so you can go for this table just to check. Okay, but anyway, so let's see if how can we do algebra manipulation to prove that these two expressions are equal. As I told you, you have the choice. I can take this term and then I use the rules I explained before. Yeah, these rules here I explained before to manipulate this term to get this term or this expression. Or you can take this expression and then you can do algebra manipulation to get this one. Okay, so that's why you need to know the rules. Now I'm gonna do it in both cases just to show you. So in the first case here, I'm gonna take this one as you see here, and then at the end I'm gonna do manipulation to prove this expression is equal to this expression. I will do it again here. I'm gonna take this one, and then I will show you how when I do algebra manipulation and I take this term, I can get this term. Okay. So anyway, either way should be okay. Whatever you think it's easy for you. Okay? So let's start with this one. So here, one of the things is one of the theorem I could do distribution. So here I can simply do distribution. So I can take this one here. I can just do distribution, and I can also do distribution here. Okay. So this one is equal A B prime or A C. Okay. Or C B prime or C and C. Okay. Also, one of the rules, you know, C and C is C. Okay. X and X is X. Sorry, is X. Yeah. So if you see, if you can find it here, yes. Yeah. What is it? Yeah. Okay. Anyway, so this is the manipulation I did here, and now, and this is very important thing, guys. In exams and quizzes, always try to look for a common factor. Okay. So and that's what I did here. You can see common factor here. I can see this one has C, this one has C, and this one has C. So I can take C as a common factor. This is the opposite of distribution. Okay. So it becomes like this one here. If I do distribution, I will get this one again. Okay. And one or B prime or A, this one is actually equal to 1. So if you have or and one input is 1, so I don't care about the other inputs. The output is 1 regardless of the other inputs. You know what I'm saying? This is also one of the rules here. That's why this one is 1. Okay. 1 and C is C. So by this way I can get it this way. Okay. Any questions? Okay. Here I will do this proof in an easier way. Okay, a much easier way. Still, I'm gonna take this one and reach to this one. Okay, I will do the opposite as well, but let's do it in a different way as you see here. Okay, so look here how I made it. A or C, it's the same like C or A. It's the same thing, right? B prime or C, it's the same thing like C or B prime. Okay, but I made it this way so that you can notice that C here is a common factor, and I can take it as a common factor. Okay, so this one actually becomes like C or A B prime. Okay, so it's also distribution. And remember, I told you this is a tricky one because we don't have this one in normal algebra, but we have here. In normal algebra, if you have 3, for example, times x plus y, I can say this one 3x plus 3y. Okay, that's what we do. This is okay. Also, we have this one here. What we don't have in normal algebra is if I say 3 plus x or y or x times y, for example. Okay, I can't say this one is equal to 3 plus x times 3 plus y. You got what I'm saying? I can't do this, but we have this one in Boolean algebra. Okay, sometimes I forget, even myself, sometimes I forget it because we don't have it. Okay, guys, so yeah, so it's very obvious here. Somehow I overcomplicated it here. Here I was able to do it just in one step. Okay. By the way, I can take this one to prove it equal to this term, equal to this term as well. Look how I can do it. I can say this one here, A, B prime, or C is equal C or A, B prime, right? It's okay if you can just switch it. But this one will help you too much because I can do distribution here. So this one should equal C or A and C or B prime. It's done. I'm done. You got it? So there are different ways. Anyway, so I have another example here. In this example, I give you two functions, f1 and f2. This function here is x or y prime z, and then we have here this function as well. So every function is actually, we have three variables, x, y, and z. And then here I'm asking you to check if these two functions are equivalent, okay, using truth table, okay. So when I created the truth table, as you see here, I just, again, I put all possible cases for x, y, and z, and then I have to calculate f1 and also I have to calculate f2. And as I told you in exams in anything, it may be difficult to calculate f1 directly. Maybe you need to add one column here for y prime, and then add another column here for y prime z. You got what I'm saying? Even if you do that, and you make a mistake, I will give you some partial marks. So every step you do in solving the question, you will get some points for that. Okay. Same thing for this one here. You need to calculate every column. Okay. Anyway, so after I calculated, I found this is f1 and this is f2. So if you see here, this one is equal to this one. That's okay. This one is equal to this one. This is okay. This one is equal to this one. This is okay. But these two are not equal. These are not equal. Okay. By the way, if in exams in anything, you don't need to continue. You don't need to continue. Once you find only one row, it's not equal. So the conclusion is these two functions are not equal. They are not doing the same thing. Okay. Any questions? Okay. The other thing here we have here is an expression simplification. Yes, sure.
If we were doing a truth table on an exam, if we hit a value that was unequal, would we have to continue at all? Or could we just say these two expressions are unequal?
Yeah, it depends on the question. If I ask you the question, just to check, okay? Just to check. Yes, once you find one value that's not equal, you don't need to continue. You already know it's not going to be equal. Okay? But if I tell you calculate f1, calculate f2, it will be different. You know what I'm saying? But if you want to check if it's equal or not, it is enough to find only one case. One case is enough. Okay? That does not give you the same result to conclude the two functions are not equal. Okay? Good. The other thing here, guys, I told you we can use, there is something we call expression simplification. So what do you mean by simplification? That's different from the English name. I can simplify a function. Okay, for example, these two functions here, this one here is when these two functions f2, which is equal x prime y prime z, or x prime y z, or xy prime, and this function, which is xy prime or x prime z, these two functions are identical. They do the same thing. You got what I'm saying? They do the same thing. So let me ask you a question. If the two functions, so I can take this function here, I can simplify it and to get this function. So this function is the simplification of this one, or simplified version of this function. So simplified means, so number one, it means these two functions are equivalent, are identical. They do the same thing. But one of them is more simplified than the other one. What do you mean by simplified? Can you tell me what you mean by simplified? Simplified means, number one, you can have fewer number of terms. So this one, how many terms we have here? 3 terms. This one has 2. So this is one way to simplify. So when you simplify, it can be you can have less number of terms, okay, or and, okay. So you can reduce the number of terms, and also number 2, you can also reduce the number of terms in, the number of variables in the terms. That means here I have three terms. I can also get here three terms as well. However, this term had three variables. This one had three variables. Okay? I may be able to reduce it. Instead of three, it becomes two. This is also simplification. Okay? So again, simplification means either you are going to reduce the number of terms, or I'm going to reduce or and. So you can do both. Okay? So this is simplification. Reduce the number of variables in terms. Okay? So now the question is that we agree simplification means I'm going to get another function. So I have this function originally, I have this function here, okay? And then I'm going to do algebra manipulation. I'm going to get an equivalent function that has less number of terms or less number of variables in the terms. You got what I'm saying? But the two functions are equivalent. They are the same. They do the same thing. Okay. So why this simplification is important? Okay. So if you have that choice, you know this function and this circuit are identical. Which one is better for me to implement? Should I implement this one or I implement this one? Which one is better? I know they do the same thing. So which one is better for me? The simplified one, right? Because the simplified one, I will need less number of gates. Okay, so that means less number of chips. That means it's going to be cheaper. That's why simplification is important. So simplification can reduce the number of gates you need to implement the circuit. For sure, that's something very important. It can reduce the cost. Okay. Also, sometimes, not all the time, sometimes it can make it faster. It can make the circuit faster. It can do the calculation faster. Sometimes it does not impact the speed, but impacts the number of gates. Okay, can you clarify? Yes, I will clarify. Look here. For example, here, it's very obvious here, because of the simplification I did, I was able to, number one, instead of using 3 AND gate, I'm going to use only 2. That's number one. Make sense? Number two, instead of using here 3 inputs, because the 3 input gate is going to be more expensive, or it needs more circuit than 2 input. 2 input is cheaper, okay? Or it needs less hardware, okay? This is also simplification. So it's very obvious here when I use this one, I was able to reduce the cost because I was able to reduce the number of gates, okay? And also the inputs of the gates. So this one is going to be cheaper than this one. But now, let's look at the speed. Is this one faster than this one, or it has the same speed? Okay? I told you, it may not impact the speed. Okay? So it may be the same speed. Okay? It may be, no, sometimes it's faster. Okay? So that's what you keep in mind. So it depends. So let's see how I can calculate the speed here. Very simple. When you put some input here, how much time is going to take to get output here? Is that okay? This is the speed. How much time? It's going to take some time. And this is what you are measuring in the lab. Okay? So don't think if you just apply an input, you will immediately get an output. No, there is a delay. And that's what you are measuring in lab. Okay? So let's see how I can calculate the speed here. Number one, when you apply input here, there is a delay time here. So I have to wait until I have TB here, delay time. Just for simplicity, to make it simple, I'm going to assume all delays are the same. Okay? So I need some delay time here until I get the output here. Okay? Also, after this delay time, after I get the output here, I have to wait until these gates give me another delay time here. Okay? They are parallel, so they work in parallel. You got what I'm saying? I don't care about parallel because they are going to work at the same time. I only care about series. You got what I'm saying? Because in series, these gates here they have to wait until they get the result here. Okay? But in case of parallel, they are going to work at the same time, so it's going to be the same TP. Okay. And then I have to wait here another TP here to get this one. So in total, around I will need something like 3 TP, okay? Because it's three levels in series, okay? And usually you have to look at the longest path. Sometimes, for example, if you look at this one, if you take this path here, this path is only 2 TP, but we don't count on this one because to get the final result here, I have to wait for the longest path. So you have to look at for the path that's gonna need more time. That's why here I can say roughly this circuit will need 3 TP. Okay, assuming again I'm making just an assumption here, all delays are the same. Just an assumption. Okay, it may not be the case, but this is what I'm just simple assumption, or maybe the difference between them is small, whatever it is. Okay, let's look at the case here. So it's the same thing here. We have to wait here for TP to get the output here. We have to another TP and then another TP here. So regarding speed, this one also is 3 TP. So this simplification may not have big impact on the speed, but for sure it has big impact on the number of gates, okay, or the hardware I need. Is that clear? This is not always the case. Sometimes you can have again in the hardware and also again in the speed. So it's not always the case. Any questions? Yeah, for example, when I simplify this one here, just an example, and this circuit here is identical to this circuit. So this one here is identical to this one. Okay. So here it's very obvious here. I can have a gain in hardware. Also, I can have a gain in the speed because here I only need TP. But here, if you look at this one, we have here 1 TP, okay, another TP here, another TP here, 3 TP. So this one can be simplified, and also it needs less hardware. Any questions? Okay, so let's make it simple, guys. Number one, the first thing, let's summarize what I said, and this is very important. Let me summarize what I said. Number one, you should know what I mean by simplification of a function. You should know what this means. It means I have to find an equivalent function that can do the same thing, equivalent function, but this function has less number of terms and also and or less number if I make it the same terms, okay? But I can reduce the number of inputs, variables, okay? This is the first thing. What we mean by simplify. Number two, okay? Why simplification is important? Yeah, it's important because the two expressions are doing the same thing. So I need to, one of them is the simplified one actually is gonna need less hardware. That means it's cheaper, which is good. And sometimes it's also faster. Sometimes it's also faster. That's why we need simplification. Is that okay, guys? Number three, how can we do simplification? Okay, I have a function. How I can simplify, how I can pick up. So now you should know what is simplification and you should know why simplification is important. That's number one. Number two, how can we do simplification? Okay, to do simplification in this chapter, I'm going to explain how can we do simplification using algebra manipulation. So using the rules we have here, I can use it to simplify a function. And this is what we are going to do in chapter 2. Okay? In chapter 3, I'm gonna explain another way. We call it Karnaugh map or key maps. Okay, this is a graphical method. Maybe this one is easier than this one to use. Okay, to do simplification. This will be the topic of chapter 3. So chapter 2, I will do simplification using algebra manipulation. In chapter 3, I will explain another way, which may be easier way or whatever, using key maps. Okay, so both of them should give you the same result. So I'm expecting you need to know both of them. Also, if I give you the choice, always you will go for key maps because maybe easier. But for you need to know algebra manipulation. Okay, so in exams, I can ask you, you have to do simplification using algebra manipulation or using key maps. Any questions? Okay. This is until chapter 3, you will learn how can you do simplification. Starting from chapter 4 until the end of the course, I will start teaching circuits, logic circuits. And then when I teach logic circuits, I'm going to use the simplification, I'm going to use manipulation, I'm going to use what I explained in chapter 1 and 2 and 3. Okay. Any questions? Okay, so here I have several examples. I have several examples here to show you how I can use algebra manipulation to do simplification. Is that okay? So let me, I want to bring to your attention something I have already mentioned, but very important. Again, in this section, in section 1.2, I explain some theories, some rules, how can you do Boolean algebra, or how can you do manipulation, okay? Boolean algebra manipulation, okay? In chapter 3, I used this algebra manipulation either to prove that two terms are equal or to simplify terms. Is that okay? So anyway, so nothing is new. I'm going to use the same rules just to simplify. Okay. So let's do, for example, I give you this function and then I ask you if 2 equals this one, I want to simplify it. Okay. So the first thing, always the first thing you need to look at, is there a common factor? You can take it common. Okay. So this is the first thing you can look at. So for sure you can see here, if you look at these two terms here, I have many examples here, and also in the inside Zybooks. In Zybooks, or I think you already have in the homework, you have another examples, okay? But let's see here. For example, here, guys, you can see I can see here a common term, like I can see here x prime z. I can see x prime z. Okay? So here you have x. If you are confused, very simple. I can rewrite this one here, because you know ABC, it's the same like CAB, it's the same. Okay, so I can rewrite it. I can say this one is actually x prime z and y, or x prime z, sorry, this y prime, and y. Okay, I just moved to this one here, and this is okay. I can do that. Is that okay? And now you know this one here is a common factor, so I can take it common. Okay. So if you are confused, if you go to what I explained before, you find if you have, for example, A, B, or AC. Okay. So what I can do, because this one has A and this one has A, I can do it A, B, or C. Even if you do distribution, I will get the same thing. But you may be confused here because this one is actually two terms. No, I can simply assume this is A. You can accept, and this is also A, so I can take it common. So what you take common, it does not need to be only one variable. Okay, it can be a term like this one. Okay, that's what I did. So the first step here, as you see, I found as you see here, I found x prime z common, so I take it out this case, this way. By the way, when you do something like that, sometimes it doesn't help. Okay, so I have to return it back. So okay, so it resolves the problem. But here helped me. How it helped you here? Because you have y or y prime. Y or y prime is equal to 1. This is one of the rules. You got what I'm saying? You need to know these rules. You need to know how. You have many examples here in the slide. Also, you have the Zybooks for you need to do also the Zybooks. So here, if you have y and y prime. So again, I want you by intuition. There are many things you can just by intuition. Okay, you don't need to memorize anything. Y and y prime. So sure, it has to be 1 because I'm sure one of them should be 1. You got what I'm saying? At least one input will be 1 here. Okay. So anyway. So that's why this one becomes 1 and 1 and anything. 1 and anything. So if you have and here, one input is 1 and then x prime z. Okay. So actually here, the output here x prime z. Okay. Because if this one, I get 1. If this one is 0, I get 0. Okay. Anyway, so I will explain this once, but sometimes that's what I told you. Believe me, if you don't do the proof by yourself, if you just read it by your eyes, just read it. That's easy. I can take this one, I can put this one, and then you come to the exam, you will not be able to. It's going to be difficult for you to use these rules. Okay? Because in the quizzes and exams, I will give you this slide. Okay? But I'm sure 100%, even if I give you this slide, if you don't practice, you will not be able to know how to use it. Okay? That's why I advise you need to practice, you need to don't just read the proofs, try to do it by yourself. Okay? Very important. Because when you just read it, yes, it's easy, but when I ask you to do it, it may be difficult. Anyway, so, and then I came to here, okay? Is there anything I can do here? This is x prime and this is x. I don't think we have any, there's nothing else I can do here, okay? This is one of the difficult parts in the algebra manipulation comparing to the maps. In the maps, it's easy to know if this is the most simplified version or not in maps. Okay, so that's why if I have the choice, I will go for maps. But you need to know algebra manipulation, and I will force you some exams. I will tell you use algebra manipulation because you need to learn it. Okay, but if I have the choice, I will go for maps because honestly. So one of the things here, once you get something, it may not be the most simplified. Maybe you can do some operations more to simplify more, and you may not be able to know. You may think it's the most simplified, but it is not. In maths, it's easy to know if it's the most simplified or not. It's much easier than here. Anyway, so let's have another example here. And I want to simplify this one: a prime, b, c, and a prime. Okay. Again, the first thing you need to look at if there is any common factors here. We have a prime when you have e prime here. I can simply take a prime common here. So a prime, b, c, or 1. Anything or 1 is 1. So if you have, for example, b or bc or x or xy or whatever, or 1. Okay, everything is 1. That's what I'm saying. So here, this one or 1 is 1. Okay. So the result is a prime. So that means if you have a function like this one, and you have this one, although this function has b and c, okay, and a, but actually the result only depends on a. So b and c are not going to contribute to the result. Let's see one more here. So again, x, y, z or x prime y, z. Again, you have to look for common factor again. So you can find here y, z and y, z. So I can take a common factor as a common. So this one y, z. So here x or x prime. You know x or x prime is 1. Anything and 1 is 1. So this actually y and z. So these two functions are identical. Okay, guys? And very simple. If you want to make sure you did it, if you want to make sure these are really equivalent, you can go to the truth table and check. You will find both of them are giving you the same result. But the truth table can prove that they are equal, but the truth table is not going to tell you if this is the most simplified version or not. You understand what I'm saying? So if I get something here, and you may think this is the most simplified, but actually there's some operation to simplify it more. The truth table can tell you, yes, this one is equal to this one or not. Okay? But it does not tell you this is the most simplified or not. Okay, but anyway, K-maps is much easier to get the most simplified version. Okay, let's have more examples here. So here, for example, I have A, B, or C, B prime D, or C prime E, or whatever here. Okay. So number one, I have an observation here. You can notice that this term and this term are identical but inverted. Okay. So they are the same but inverted. So if I call this one y prime, this one becomes y. If I call this one y, this one becomes y prime. So whatever you do, they are the same but inverted. So this can be the inversion of this one, or this one can be the inversion of this one, because the relation between them is inversion. So I can notice here, this term together, actually, I can call it y prime. And this term, the whole term here, I can call it x. Okay? And this term, I can call it y. So now, my problem became y prime x or y. Okay? And you know, from y prime x or y, this one here is actually equal to x or y. This one of the rules we have before, I'm proving it here. I don't need to prove it because I think this was one of the proofs we had before, but you can prove it. So if you have y or y prime x, so I can do distribution, it becomes y or y prime and y or x. Okay, this one is 1, so it actually becomes y or x. Okay, so I can say here, so the result here should be x or y. So I can, and this is x, so now this is x, and this is y. It may not be this most simplified, so you can actually, this is a difficult part here, as I told you, okay? You can actually, you can do De Morgan here and to try to simplify it more. You can see if you can or not, but at least what I want you to learn in this example, as I mentioned many times, if you have one expression, I can say for the sake of using one of the rules we have, I can put this part, for example, it's y, and this part is y prime, and so on. You got what I'm saying? But is that true to say, is this true to say this one is x? Some answer for sure, yes. You know why? I'm going to tell you why. Because after you do the calculation, this term should be 0 or 1. Same thing for x. X is a variable. It can be equal to 0 or 1. So yes, I can do that. Okay? Anyway, let's see another, any question here? Let's see another example here. If I have here these two terms here, for sure, some students may overcomplicate it and then they start to do distribution. So you can start to do distribution, okay? For sure you can do that, but maybe there is a shortcut, maybe there is a much easier way. And you may even reach to the same solution. Okay, so similar to what I did here. So if you remember in the first one here, in the first one here, I did distribution and I wasn't able to get the solution. It was possible just to do it in one step. Okay, that's why algebra manipulation is not as easy as maths. Maths are much easier, to be honest with you, but still you need to learn algebra manipulation. Okay, but anyway, so if I notice here, if don't rush and just do distribution. Okay, try to think a little bit. So for example, if you look here, I have observation that this term here is identical to this term, and this term is actually the inversion of this term. Okay, so in this case, if I put this one x, if I put this one x, so this one becomes x. If this one is y, this one becomes y prime. Or if I put this one y prime, this one becomes y, because the relation between them is inverted. Okay. Anyway, so now I have x or y and x or y prime. So this is the uniting theorem. Okay. So actually here x or y prime, right? So you can just use the theorem. You have the theorem, or I can prove it quickly. How can you prove it quickly? I can take x or as a common factor, so it becomes x or, okay, y prime. Y and y prime is 0. 0 or x, the result is x. Okay, so either use this theorem or you can do quick proof for it. Okay, so anyway, so that means using this one is equal to x, and x is actually this term here. So the result is this one. So just by quick observation, I can imagine when a student can do this way, it takes 0 seconds or 1 second from the student to solve the question. Imagine another student who actually did distribution and they had 100 terms, and now it's gonna make it more difficult. You got what I'm saying? Anyway, in general, maths are easier in general, okay? But you need to learn them both. Any questions? I have one example here as well. So this term is here. Again, I have an observation. I can see xz is here, xz is here, xz is here. So I can take xz as a common factor this way, and then after that, inside here I can notice there are what w here is common, so I can take w common as you see here, and then y1 or y, this one becomes 1. Okay, so w or 1 is w. W or W prime is 1, so the result is X. Okay. Let's also here, what I did here, number 1, I took this term, I just changed its location to here, which is okay, because A or B or C, it's the same thing if it's C or A or B. It's okay, it's the same thing, okay? And by the way, we have the same thing in normal algebra, right? 3 times 2 times 5, it's the same like 5 times 3 times 2. Same thing for addition, 3, so we have the same property in normal algebra. But why you take this one and moved here, same here, as you see here, I moved it here simply because I noticed there is a common factor between these two, okay? So once I come to you can see, I noticed it's a common factor here. What y prime z is a common factor, so I can take it as a common factor. Also here I noticed we have yz here and have yz here, so I can take it as a common factor. X or x prime is 1, x or x prime is 1. Okay. This is a trick. Some student may think, okay, now it's okay, now I did very good job. It was 4 terms, now it became 2 terms. And here every term was 3 input, now it's 2 input. Yes, this is the most simplified one. You got what I'm saying? It's hard here, or sometimes it's a little bit hard to know if in math it's easier to know if this is a most simplified one or not. It's much easier than here. But anyway, you can stop here and you think this is a most simplified. No, we can do more. Okay, as you see here. So what you can do here is, again, you can notice here when you end with 1, you will get the same value here. Anything and 1 is the same thing. Okay. So you can notice here we have here z and z, so I can take z as a common factor. So y prime or y equal to 1, so now z. Very interesting. So look, this big function is actually equal to z. You got what I'm saying? By the way, if you go to the truth table, you can notice what you can notice. I can notice the column of this function is identical to the column z, because they are equal. You got what I'm saying? So if you implement this function, if you do it using truth table, look at the column here, you find it is identical to z, the column of z. Any questions? Okay, good. So I have more examples here. Let's do these more examples. That's okay. For example, I have here this example here. So again, we always try to force something common. So here I can see here we have EB prime, so I can take it common here. That's what I did. Okay. Also, same thing here. We have EB and we have EB here, and I take it common. Now, C prime or C is 1. This one also is 1. When and anything is the same thing. So now it became like this one. Okay. Is this the most simplified? This is a difficult part. Is that okay? You may be happy. Okay, look, I make a big reduction, but this may not be the most simplified. Maybe you can do more. So that's what I'm trying to do here. For example, also I noticed this one has A and this one has A, so I can take A as a common factor here. And once I do that, so this actually becomes B prime or B. This one is 1 and A is A. Okay, so now we are here. Okay. Maybe the coming part is somehow the difficult part, because again, algebra manipulation is difficult. It's more difficult than maths. Maths are just easy. It's a visual way, as I'm going to explain in chapter 3. Okay. Honestly, 90% of the people, you may stop here. Okay, when you come here, you may stop here and think this is the most simplified version. But actually, you can actually simplify it more. So look how how I simplify it more. Okay, look here, I can rewrite this way. So I can just A plus. I didn't do anything. I just wrote A before. Okay, A prime BC. Is that okay? And now I can do distribution. I'm gonna consider this one like one term, and this one is one term. I can do distribution. So when you do distribution, it becomes A or A prime and A or BC. And now this term is one, right? So one and anything. So now I can actually simplify it more. Why I'm saying most of the people when they come here, they stop here, simply because we always forget this property because we don't have it in the normal algebra. The distribution, this one we don't have in normal algebra. So anyway, let's have another example here. Okay, so I'm going to simplify y2 here. Okay, so in the very beginning, you can see here we have, for example, here C and C prime. C and C prime is 0, right? C and C prime is 0. 0 or anything is the same thing. So that's why I can just cancel this term. Okay, so now we have this one here. Okay. And now after that, what I'm going to do now is, for sure, the very easy way, you can just do distribution. So this one is going to give you 3 terms, and then you can have 3 terms here. Yes, you can do that. But I had an observation here that may help you. The observation is, I'm going to take, so I just A or C. You can say I didn't do anything. I just put C before B prime. Okay. So from here to here, I do rearrangement. Okay. So here and then after that, so I'm going to consider this one like one term and this one like one term, and then I do the distribution. Okay. So here I make this distribute here and distribute this one. I can do distribution this way. Okay. And then after that, when you, so here you have, so here you have B prime, so I can input here B prime and I can input here B prime. So this one becomes B prime, AB prime. Here, I can have the observation that I can take A plus as common factor. You know what I'm saying? Again, A or BC equal to A or B and A or C. What I'm saying, this is so here, if I here, I can come here. If I'm here, I can come here. Okay, so now I'm doing the opposite here. Okay. Again, this is somehow a trick. I did it here so that I make it simpler. Okay. But you can take the straightforward way. You can just do distribution and then you try apply the rules. Yeah, this one, like a shortcut, make it more simple. Anyway, so now I'm here. This is the most simplified, or I can do more. Yes, I can. For example, this one, I told you this one is 0. Okay. And now we have A or AB prime and BC. I just change the order, which is totally fine because I want to take A as a common factor. So now I can take A as a common factor. So now it's A, one or anything is 1. 1. So this part should be 1. 1 and anything is the same thing. 1 and A is A. Okay, by this way, I was able to get the most important. Any question? Okay. So usually what I will do in quizzes, I'm not gonna tell you simplify it, because if I tell you simplify it, I will not be easy, because you may come here and you may think the most simplified one. I will not just tell you simplify. What I will do usually, what I do just to help you, I will ask you prove that this one is actually equal to this one by simplification. Or I can say simplify this one and the answer is this one. You got what I'm saying? So that when you reach to somewhere, you can know this is, I'm just helping you. You need to, it's not, I can do more work. I can do more work to simplify it more. So I will give you the answer, okay? I will give you the most simplified version to help you. Otherwise, you may reach to some expression and you can stop there. Anyway, any questions? Okay. The next thing here is what I explained to you De Morgan. You remember De Morgan when I explained to De Morgan? De Morgan was A or B if you complement it. So this is actually is you complement the first one, you complement the second one, right? So A prime, B prime. And if this one here, if this operation is OR, you make it to make it N. If it is N, make it OR. You got what I'm saying? This is De Morgan, how De Morgan works. And also, I told you in case of De Morgan, it can work for more than 2 terms. So if it is A or B or C, still it can work for any number of terms. So here in this case, if I use De Morgan here, so I'm gonna get A prime and B prime and C prime. Okay? So every term need to be complemented, and also any OR you have to make it N, any N you have to make it OR. Okay? One more thing you should know, it does not, again, as always we do, it does not need to be individual variables. For example, it can be AB or CD inverted. So this is one term, so you have to invert this one, AB prime, and CD prime. Yes, it can be a formula. Okay? And then you can use De Morgan again here. Yes, you can. So this one becomes A prime or B prime and C prime or D prime. Okay? So here's what I'm saying here. I'm explaining complementing a function, Boolean expression or a function. So if you have a function like this one, F1, and I wanna get the complement of this function. Okay, complement of this function. So complement means you can just so if this is a complement of this function, so I'm gonna take this function and then I'm gonna complement it. Okay. So and after that I can apply De Morgan. So this is one expression here. This is one term and one term. Okay, and then I'm gonna apply invert the first term, invert the second term, and then OR becomes AND. Okay, and then I can apply De Morgan again with this one here. I can apply it again. So this one becomes invert the first term, invert the second term, and becomes OR. Okay, so this one Y prime, when you invert it, you get Y. Z, when you invert it, you get Z prime when you invert it. Okay, so again, what I'm explaining here, guys, it's very easy to get. If I give you a formula or a function, and I ask you to calculate the inversion of this function, you need to apply De Morgan. Okay, I explained De Morgan before. This is number one. Number two, what it means when you have a function, you have the complement of the function. What it means in the truth table? It means, if you look here, if you have F1 here, so F1, the complement, so everything is complemented. Makes sense? This is the meaning of complement a function. So if you have here a circle, and you have F and you have F prime, what it means? Okay, it means if this one is 1, this one becomes 0. So you have two outputs. One output for F, one output for the complement of the function. So complement of the function. So as you see in the truth table, this is the meaning of it. Meaning of it. So if this one is 0, I'm gonna get 1. 1, I'm gonna get 0. 0 if you want, and so on. Okay, guys? Any questions? We'll have something related to this one later in this course. For example, we have something called flip flow. In flip flow, here I give you Q and also I give you Q prime. So I give you the output and the prime of the output, both of them. And then it depends on what you want to do. Okay, I may use this one or I may use this one. You understand what I'm saying? So the meaning of it is I have the output, I have the function, I have the complement of this function. Sometimes in one design, I want to use this one. Sometimes in one design, I'm going to use this one. But you should understand what complement means. Two things here. Number one, you should understand what complement means. It means if the function is 0, the complement gives you 1. If the function is 1, complement gives you 0. Okay, and that's true here for everything. That's the meaning of it. Number two, you need to learn if you have a function, how can you calculate the complement of this function using De Morgan? Okay. I think I have more examples here to apply De Morgan. Here I give you this function and then I ask you to calculate f prime. So as you see here, this is the whole function prime. Again, very simple. you need to apply De Morgan. De Morgan is telling me this is A and this is B. So I have to complement the first one, I have to complement the second one. Any and has to be, any or has to become and. And that's what I did here. I complemented the first term and I complement the second term. Okay? I can continue. Okay, so here I can take this term, here I can continue. So here I have three terms. I have three terms ended together. So I can complement the first one, complement the second one, complement the third one. Okay, as you see here, so x prime becomes x, y becomes y prime, z prime becomes z, and then any end has to be or. Okay, same thing here. We did this one as well. Okay, so here this one x prime, x prime prime, it becomes x, y prime prime becomes y, z prime becomes z, and then prime should becomes z prime. Any end should become any end become or. Okay, and then after that I can do simplification. So what I did here, I did distribution. So now I'm gonna have how many terms? I'm gonna have 6 terms. Also here I'm gonna do distribution. I'm gonna also do distribution. Okay, this is a straightforward thing. Okay, so I can just do distribution. Maybe there is some shortcut or maybe easier ways. Okay, so for example, I can notice here. I don't know, but you can think about it. So for x, I may not help you, but I found here x prime. I can take x prime common, but it may not help me. Anyway, so then it becomes y plus or z, and it with y over z prime. Yeah, so you can do this way, and then you try to simplify it or more, or you can just let's use the very basic way I did here, the very basic way or the easy way. I just did distribution, and now I want to work on this terms here. Luckily, I found this one is 0, y and y prime is 0. Okay, z or z prime is 0, so I was able to get rid of 2 terms. Okay, so now, and then after that, always try to look for something common. So I found here x is common, x is common, x is common here, x is here as well. Okay, this will become a big hit. X is here. So in all of these terms, I'm gonna get x as common here. Okay, when I take x as common, 1 or anything, all of this becomes 1. So I was able to get rid of 5 terms, okay, or 4 or 5 terms here, just because I took x as common here. So x is common. When you take x as a common, so here this one becomes 1, this one becomes y. Okay, so this one becomes 1, this one becomes y, this one becomes z prime, this one here becomes y prime, this one becomes this one here becomes z. Okay, x prime. Okay, so after that, how many? So still I have this term here, until I have this term here. And one or anything. So all of this should become 1. That's what I did here, becomes 1. Okay. So now this is I was simplified this way. Okay? Just to prove I did it correctly. Also, truth table can help me to prove that. Okay. So look how I made it. If I want a truth table to prove actually this one is actually f prime. I want to prove this one is f prime. I have f here. And I want to prove this one is f prime. How I can do it? Very simple. Again, I have x, y, z. I have to calculate f here. I have to calculate f. To calculate f, I need to make 1 column for this one for this one, as you see here. Okay. And to calculate this term, I need x prime. So you need to make a column for x prime. Z prime also you need this one z prime, and also you need y prime. Anyway, so I was able here. You can see I have 1 column for f. So given f here, I have the function of f. I need to make column for f. Now, given any f, I can easily make f prime. So given f, I can easily make f prime. How? Just flip the bits. If f is 0, f prime should be 1. This is 1 becomes 0, 1 becomes 0, and so on. Okay. Now I just want to make sure. I want to check if this one is true, this f prime. So I'm going to implement this one here, and I have already f prime. If you compare, you will find they are equal. So it is true. This one is f prime of this one. You understand what I'm saying? So let me say it again, what I did. Here, I have F. I did some operation, and then I got an expression here. I want to make sure this expression is the inversion of this expression. I want to make sure this is true. Okay? So very simple, very simple. You have F. Number one, I need to make a table for F because this is given to me. So this one, I'm going to get F. If you have F, I can make F of prime. Is that okay? And then I'm going to implement this one here. Okay? And then I can check if they are equal or not. Yes, they are equal. Any questions? Okay, good. I have one more example here is about how can you complement, how can you calculate the complement and you can simplify. For example, here guys, I want to calculate the complement to this expression here. Okay, so I can simply think about it. So again, De Morgan, how? So you know De Morgan, but how can you use it? The way I'm going to use it is, look here guys, I have one term here, I'm going to call this term X, and then I have another term here, I'm going to call it Y. Okay? So X, Y, so actually, and it is N. So this to De Morgan, it has to be X prime or Y prime. That's what De Morgan told me. Okay? Now, Y is actually here C prime. Okay? X actually is A prime or B. Okay? That's why it becomes this way. Okay? And now, I can inversion of the inversion, I'm going to get C. Okay? And I can apply De Morgan again here. I can apply De Morgan again here. You have one term or one term. So I'm going to invert the first one. I'm going to invert the second one. Any order should become 8. That's what I did here. Okay. Same thing here. Same thing here. Look here, guys. Again, how can you apply De Morgan here? Okay. You can apply it in different ways, by the way. So I can take the whole term here as X. I can take this term as Y. Okay. And then I invert the first term, invert the second term, and then any order should become end. So I can apply this way. And then after that, I can apply De Morgan again here. When I apply De Morgan again here, this one becomes X, and this one here becomes Y. Okay? So here I invert this one. This term was D prime, it becomes D. Okay? This term here, I'm going to take this term and invert it. Any end should become O. Okay? Okay, and still I can break it more using De Morgan again. I can break this one more using De Morgan. Okay, so here you have X and you have Y. So I need invert this one and invert this one. So if I invert this one becomes C prime. Any O should become 8. Okay, I can apply De Morgan again. Look how many times I apply De Morgan. So still, because this one here, I can apply De Morgan here again. Okay, I have one term X, I have Y here. So I have to invert the first one. I have to invert the second one. Any end becomes O. Okay, so I can do this way. By the way, you can do it in a different way. You can, from the very beginning, what you can do here from the very beginning, you can do distribution. Okay, maybe easier, maybe whatever, but you are going to reach to the same conclusion. So I can say this one becomes A, B prime, D prime. I can just do distribution. Okay, or C, D prime, or E. Everything here is inverted. Okay, and then I can apply De Morgan. When I apply, I told you for De Morgan, I can apply it for 2 terms, 3 terms, 4 terms. It works for any number of terms. Okay, so here should equal to the first term here, A, B prime, D prime. Everything is inverted, and any O becomes N. C, D prime inverted, and E inverted. And then I can take this one, break it more, take this one, break it more. Okay, you can do this way. Maybe I overcomplicated it, but you should be able to reach to the same conclusion here. You should be able to reach the same conclusion, but maybe it's going to take longer steps. Any questions? Okay. So in next section here, I'm going to talk about more gates and logic chips. It's very related to lab number 3. Okay, I posted lab number 3. Lab number 3 will be done next week. Also, I need a video for lab 3. Okay. So in the very beginning, I was very clear, guys. I told you we can implement any logic circuit using 3 gates, right? So I was very clear about this. You can use inverter, you can use AND, you can use OR. So any computer system can be created using these 3 operations. Any logic circuit can be created using these 3 basic operations. Is that what we agree on that? Okay. Now, I'm gonna use this 3 basic operation to create gates, okay? And then I'm gonna use them as gates. But this gate can be broken down into these 3 operations. So using these three basic gates, I'm gonna drive or I'm gonna create more gates. One gate here, we call it NAND. You can see I use the same symbol of AND, but I put bubble at the end. Usually in logic circuits, this bubble means inverter. So this bubble, when you see bubble, sometimes, for example, if you have AND this way, so this means inverted, right? We know this symbol, right? But sometimes you put bubble here, it's the same. So sometimes if you put bubble here, it's the same if you use inverter here. So usually this bubble means inverted. Anyway, so this is the first gate, NAND. Also, we have NOR. You can see here, it's the same symbol of OR, but I do inversion here, or I do bubble here. Also, we're gonna do something, we call it XOR or exclusive OR. Also, we're gonna make another gate. I'm gonna call it exclusive NOR. Okay, so again, we started with the 3 basic gates. Using these gates, I'm gonna create 4 more gates, and then I'm gonna use it as a gate. But to create this every gate here, I'm gonna use these 3 basic operations. You got what I'm saying? So I'm gonna create 4 more gates. I'm gonna use them as a gate, but these gates are created using the 3 basic operations. Is that okay? I use it as a gate. So here again, the four gates I'm gonna explain is NAND. So now we have a NOT or inverter, we have AND, we have OR. So now I'm gonna add 4 more. We have NAND, we have NOR, we have XOR, exclusive OR, we have exclusive NOR. Okay? So let's see how they work. So the first one is NAND. So actually NAND is actually not AND. So actually this gate, so this one, okay, this gate is called NAND. Okay? So actually this gate is equivalent, as I'm very clear. We have 3 basic operations. Any gate, anything we are going to create, they are going to be created from the 3 basic operations. So actually, this one is equivalent to AND and followed by inverter. You got what I'm saying? So if you have AND and followed by inverter, this one here, I'm going to call it 1 gate, like NAND. Now understand, it's not 2 gates. I'm going to create it using NAND. Okay? Any questions? Okay. So now, if you see NAND, so NAND gate is actually AND followed by inverter. Okay? Now, let's think about the truth table, how it works. Very simple. It's the same truth table of AND, it's the same like AND, but you invert the result. Okay? How AND works? The way AND works, as I told you before, if one input is 0, output is 0. That's how AND works. The only way to get 1 when all inputs are 1s. That's how AND works. Okay? Now, because there is inversion, so I'm going to use the same truth table, but I'm going to invert it. You got what I'm saying? So now, if one input is 0, okay, and give me 0, inverter make it 1. You got that? Very easy, right? Inverter make it 1. So if one input is 0, I'm going to get 1. Okay? The only way to get 0 here is when all inputs are 1s. Because when all inputs are 1s and give me 1, inverter make it 0. So that's why if you look at the truth table here, If one input, okay, we are done. Just why you are laughing? Okay. So, anyway, so okay, I will do it next time. Okay.